So let's now think about the situation we find ourselves in when we are working with an inconsistent system. The situation is that we have some vector b that's in our system representing the augmented column, and that vector is not in the column space of our matrix. Well, what do we do when we have a vector that we want to be in a space but isn't in the space? We project. So this is the idea behind projections. We can project a vector b that's not in the column space of a matrix onto the column space of a matrix, and that gives us an equation. The equation is that the projection pb is equal to some linear combination of the columns of A, which is represented historically by A times some vector x hat. So the idea is that we're going to drop a perpendicular, an orthogonal ray from B to the column space of A here. That defines the projection, and the projection is equal to A times x hat here. So this capital X here should say A. Well, how do we figure out what x hat should be? Well, what we want to do is we want to look at this difference vector here. This is the difference between B and A minus x hat. We go against the projection and then with B here. Because this is a projection, this difference vector is orthogonal to the column space of A. And remember from orthogonality, if a vector is orthogonal to the column space, it must live in the left null space. So B minus A times x hat must be in the left null space. But if we're in the left null space, that means we satisfy an equation. When I multiply by A transpose, I must produce the zero vector. So A transpose multiplied by B minus A times x hat must equal the zero vector. But if I clean up this equation by distributing A transpose, I end up with the equation A transpose A, that's the Gramian of A, times x hat equals A transpose times B. So the x hat that we're looking for, which tells us what linear combination of the columns of A gives us the projection, satisfies the equation Gramian of A times x hat equals A transpose times B. And this is the theory behind this concept of least squares. So let's introduce some terminology here. If we're studying a system AX equals B, we say that the associated least squares problem of that system is the system A transpose A times x hat equals A transpose times B. The variable here, of course, is x hat. And what I want everyone to see here is that, but when we're looking at the associated least squares problem, we're looking at a new system, and the coefficient matrix is the Gramian of A. Now, any solution to the least squares problem, x hat, is called a least squares approximate solution. And those are the vectors, x hat, that satisfy the equation A times x hat equals P times B, where P is projection onto the column space of A. When we're working with least squares, there's a notion of error, and that notion of error, E, is the square length of the difference between B and A times x hat. So this is the square length of B minus A times x hat. That's called the error in the least squares problem. So let's look at an example here. Here I have a 4x3 matrix A and a vector B. I happen to know that the system AX equals B here is inconsistent. So what do? I look at the associated least squares problem. So the least squares problem is a system where the coefficient matrix is the Gramian of A. And the vector we're augmenting with now is A transpose times B. To solve this system, we row reduce. So now I row reduce the least squares system, and I get this reduced row echelon form. The original system was inconsistent, but the least squares system will always be consistent. And in fact, here what we're finding is that the least squares approximate solution to this system is 2, 0, 1 for x hat here. Once I have the least squares approximate solution, I can look at the error. And remember, the error is defined as the square length of the difference between b, which is the vector we started with, 2, 0, 3, negative 4, and a multiplied by x hat. So x hat here was 2, 0, 1. When I multiply by a, what I'm really doing is scaling the first column by 2 and then adding that to the second column. So I get 1, 1, 4, negative 2 when I do that. So when I take the difference between b and a times x hat and then look at the square length, here I get 7. So the error here is equal to 7. Finally, the last thing I want to point out here is we just multiplied a times x hat, and one of the properties in least squares says that a times x hat is the same thing as the projection of b onto the column space of a. And since we did that multiplication a moment ago, we have just found out that the projection of b onto the column space of a happens to be this vector, 1, 1, 4, negative 2.